as well. So this project in scope and complexity is nothing like that. But it was fun and it was interesting. So let me give you a little bit of background before I launch into the details. A colleague of mine in his retirement has been doing, and this is going to challenge your assumption, Dave, about large integers, has been doing a bunch of research into mathematical properties of big numbers. Mostly he's dealing with large integers at 100,000 digits and wider and doing all sorts of mathematical stuff. I don't know. It's his fun retirement play toy. He runs Pharo and occasionally Squeak on a Linux box, and even though he's got a very fast multi-core desktop machine that I built for him, you know, he's a little bit frustrated by the fact that, as we all know, at least the Squeak and Pharo line of stuff, the VMs are single-threaded effectively. Pharo actually now has two threads, but the second one's for system stuff. And these calculations and stuff take time, right? So plowing through all these things was taking, even on a 4+ megahertz Linux box, was taking, you know, an hour plus per iteration. And so he wasn't making a lot of progress. So we got to knocking around, and then he discovered, which I already knew about, raspberries, right? Now, the fun thing about Raspberry Pi boards is they're 1.2 or 3, I forgot the B pluses, are like 1.3 megahertz, 64-bit, although the software that's running on them is 32. 4-core machines, all right? So I got to thinking about this and digging around on the net, and guess what? There's companies that make neat little stackable things where you can buy multiple deals and stack up 3 or 4 or 7, happens to be the number I picked. You'll see why in a minute. And I got to thinking about the problem. So what I eventually built for him was a Pharo-based compute cluster that essentially has 28 workers, 4 per board, 7 boards, okay? So I'm going to go into how all that worked. Just at a high level, it looks like this, right? Everybody's got to have the high level pitch. His hub machine is Linux running 64-bit Pharo, and then the compute cluster is the 7 Pi boards with 28 workers. So how did I take advantage of those cores? We'll get to that. I also built the whole thing from scratch. That was the case when I was finishing the prototype and was actually running. The only commercial thing in here are the hub, the power supply, and this stackable frame I actually bought off of Amazon to put it all together. But the box and the wiring and all that stuff was all custom that I did. So from the top view, you can see the boards are stacked this way. This is an 8-port Ethernet hub. I figured having Wi-Fi all packed together like that wasn't going to work out so hot. It doesn't do, I mean, the messengers are tiny, there's not a lot of traffic, but I didn't want the Wi-Fi to be on, and these things are all running headless. So custom cut cables, which I built. Then this is an 8-port Anchor 5-volt, you know, USB power brick. 7 of the ports power the Raspberries, and the 8th port powers the Ethernet hub. It all lives inside a Lucite box, which, you know, I bought sheets from Lowe's, cut them up, glued them together, and like that. This is an edge-on view, so that's the hub down there. These are the boards you can see stacked up, but I wanted you to see you saw the holes in the top, and I actually put a couple of just PC case fans in there that are also running right in the thing. So when you plug this in, there's pretty good airflow in there. And actually, I don't talk about it here, but in the production thing, I had one instance on each of the 7 boards of a little tiny Ruby script that once every minute, I think, queried some values in the underlying board, which you can get in terms of temperature and overall voltage of the stuff, and just transfer it. And he had a separate little monitor window that was 7 little sort of stoplight things on it that ever told it if it, you know, and when it was running, the temperature would go up, but it never got anywhere near, even though we were hitting it pretty hard. Okay. So software-wise, like I said, running Pharo v6 image. The trick is that I built all this in a central image, right? And then once I got stuff running, I distributed an exact copy of that image to, well, let's back up a little bit. It's not physically the same image, but the same level of image, but with the same code. My code in all those images is identical. The images are not identical, but the code pertaining to this project. All the packages are identical in all of the images. And that is a set of classes to define the task objects, which, you know, I had some demo ones. He eventually wrote his own. He's got 2 or 3 different classes that do that, the dispatching and all that sort of stuff. I went through, and then there's a spec, is a framework in Pharo for building UI, simple UIs. So it's just a simple monitor UI that shows the currently running tasks and how long they've been running and when they answer back what their answer is and stuff. There's 4 copies of the image on each Pi, and that's how it cheats. And I'll show you in a second how that works. Some other frameworks that were important to this is I used the stamp framework. So if you guys are familiar with MQ, which harkens back to my enterprise day, there are commercial implementations of the AMQP spec that everybody uses, one of which is RabbitMQ. So I run a copy of RabbitMQ on there, and then one of the guys that contributes stuff to Pharo wrote what he calls the stamp framework, which uses Stomp, which is an abstraction layer on top of MQ that's just easier to use. It just defines simple queues and simple messaging. I tried some other, excuse me, messaging frameworks and stuff with TCP and a bunch of other junk, and it was just, the complexity got crazy, so I threw them away, and then I thought of this one night, and it turned out to be really easy to do because the messaging all shadows. Another important framework, which apparently some of you are familiar with, is Stone, which I really love, which is JSON essentially for Smalltalk objects, so that you can essentially serialize and materialize from an object to a string and back successfully, as long as your objects aren't too nested or too, you know, but it takes the state and everything too. And you'll see why that's important in just a minute. Also in Pharo, they have this announcement framework, which replaced the old Squeak event framework. And it's really nice because it doesn't use symbols. It uses the announcements are actual objects, and they can carry state with them based on the announcement and stuff. And I use that to distribute around the events that occurred, so that if the hub dispatched a shutdown command or a task command and a worker received it, the reception process, which is running in a little forked piece of code, uses an announcement to tell stuff outside, go execute this task or go respond to this command or whatever. So there's essentially a shadow set of events. There's the objects flowing on the queue who are then responded to by then distributing an announcement in response to that within the image. So it makes a very clean implementation in terms of getting essentially a message sent here being responded to over there. So it's a shadow of a Smalltalk send effectively, but through these other mechanisms, okay? And then, as I said, I used RabbitMQ to actually, so that just runs on the hub, and the other people just access it through TCP. Okay, so the structure on the Raspberry Pis is in the home directory for Pi, where N is 1 through 7. There's a Pharo directory, which has the VM, the libraries, and all that, and a magic startup script. So the VM is common. And then there's 4 different worker subdirectories which hold the image and changes and log files. And the reason for this is that when the Pi starts up, that magic startup script starts each of those images in the subdirectory using the same VM. So now we have 4 single-threaded instances of the VM running with an image, each grabbing a core. And there's a few other things going, but it's a headless machine, so there's not a lot of other traffic. So essentially, I have now just created a 4-core Smalltalk environment, times 7 boards for 28 cores. The key thing, as I said before, is the images are the same, or at least my part of the images are the same, and the workers, with one exception, never save the image, okay? So I'll talk about how that works in just a sec. So these are some pictures of just the queuing I needed. The first one was that the hub uses a task distribution queue. Basically, this is a queue where the receiver is required to acknowledge when it's done with the work, and the pressure level set to 1, so it'll only ever distribute 1 task to any unacknowledged receiver, right? So the hub can just, as results come in, can just stick a new one on the queue, and the queuing mechanism will just distribute it round robin to whoever. So like when you first start the hub, it puts 28 of them on there, and the different workers just pick them up in whatever order that Rabbit gives them to them. Okay, so that's one of the queues I use. The next one is a status queue where the workers can report back. And this is just a common, simple queue. Any of them can talk to it. The hub monitors it, takes the messages off FIFO, and these are messages like task claimed, task complete, whatever. just various status things, software updated, whatever response to that. So it's just a simple FIFO queue. And then finally, there is an exchange topic, which looks like a queue, but is slightly different in that the exchange is a concept that allows you to essentially, each of these queues are generated dynamically by Rabbit, and they're temporary queues attached to each of the workers who claim one. And what that means is it's now a broadcast mechanism, right? Anytime the hub sends out a message like quiesce, shut down, update yourself, or whatever, it fans out to all of the workers. And so they have a separate receiver process that waits for those messages and knows how to respond to them, because you need a mechanism to be able to talk to the whole cluster, right? Okay, so the hub can quiesce and reactivate workers by these commands that go over the command channel. And by the way, those I could have had a separate one, and I didn't bother. Some of the status messages that go over this queue are meant for the entire cluster, like shutdown. Everybody responds to that. There's others that are meant to be aimed at a specific machine for one reason or another. And in the contents of the message, it'll select that machine. And so the other ones will look at the header, and just when the object's reified, it just ignores it because it's not for them. But a lot of them are meant for common distribution. Yeah, before I get to that, I guess I should talk a little bit about how this works. So the consequence of having a common set of classes between the hub and all these workers is they all have the same code. They're not all executing of some of it's worker-only code, some of it's hub-only code, but they have all that code. So task is an object, right, that carries with it input states and eventually results, and it has a bunch of things. So when I want a worker to do a task, I instantiate that object, put whatever state in it needs, and there's dispatching code that I helped him write for his particular kinds of tasks to figure out what the next task should be. A number to seed the thing, some other kind of parameters that go on it. That task then gets sent to the queue, and what happens is that Stone turns it into, serializes it, sends it to the other thing. The image on the worker side reconstitutes it, right, materializes it, so it's got an exact copy of that object, which is now released over here. It's not needed anymore. So this is not really distributed Smalltalk because it's not actually the same objects, right? They're not equal, but the state's the same, the structure's the same. It's good enough for what I'm trying to do, right? The worker then works on the thing, adds other state to it, like a result, a timestamp of completion or whatever. When it gets done, sends it back on the status queue. The status is actually an object that wrappers the task that just says, I'm a result. All that is just a thing that the thing it's holding is a copy of the updated task, which again, now the worker doesn't hold, but the hub gets it back and can actually stick the state from that into the UI or into the log or whatever, right? So as long as I know that those two things don't ever get out of sync, I'm good. I can essentially distribute objects using this process. So I talked about things can be restarted, and the way the restart works is, for the demo, or the prototype that I did, I just had like a 5 millisecond delay, and it did some calculations just so there was a little random delay in there. His stuff that was taking an hour plus on his Linux box tended to run 3 to 4 hours per board, per CPU, but he didn't care. It just sits up on his file cabinet and runs, right? So they just go. But sometimes he needed to quiesce or shut the thing down, and stuff wouldn't be done. The hub knows the status of tasks that it's put out and it hasn't gotten answers for. And so basically, if you issue a shutdown or a quiesce at the hub side, it keeps marked all of the tasks that it haven't completed. And the shutdown process for the worker is that it terminates the forked loop, effectively throwing it away. So maybe it's run 2 or 3 hours or whatever. We just decided we weren't going to get fancy. It just throws the work away. And so when we restart things, the hub's smart enough to go back through and redispatch any uncompleted task. And then if it needs more, it'll go make new ones, right? So it has the tendency, you don't shut it down very often, but it would have the tendency to throw away work that was done. But again, the work's cheap to free, right? So the one exception to never saving the image is for software update. So I make changes and we want to update this thing, or he writes a new task and needs to distribute. How do you do that? Well, in development and on his machine too, we have a simple excuse me, a simple web server that's using DAP to implement a Monticello server, a repository for Monticello. And so when I'm doing development, I use the GUI to version the packages to Monticello, right, which makes the .mcz files. But you can also do Monticello stuff programmatically with message sends, right? It's got an API or whatever. And so the deal is when there's a new release, the hub machine, the development machine, will make a new version of all the packages that need to be updated, send a quiesce message to the workers. Once they all raise their hand and say, okay, I'm done, I'm frozen, what do you want me to do? Then it sends out an update command with the version string. Then they all each internally just send the right API messages to Monticello to replace the package with the new stuff. And when they're done, they go back into the ready state and off they go. But before they do that, they snapshot themselves. So now I know that the workers again are in sync with the hub because they just snapshotted the package that they loaded in there. That was sort of fun to get working. And that is that. We started working on the design of this last October, pretty much had it sketched out in the first version where I was using an actual distributed object system called Basis. Kind of had that prototype, was tearing my hair out in mid-January and threw that away. The messaging objects and all that are very simple and light. I sort of had that done. Then went through and put the code away and spent about 2 months actually building the actual thing with all the boards and the physical construction of thing and testing that all out. And then towards the end of that process, I came up with the idea of, do it with MQ. So I did all the research into that and figured out, yep, it'd be really easy. And the code for this is ridiculous. A lot of things in Smalltalk, once you get the complexity down, it's just ridiculously simple in many ways. I did a few little clever tricks like the status messages that come in. Well, all of the message objects, whether it's task or shutdown or claim or result or whatever, on their class side, they have a symbol that says what they are, right? And that symbol matches a method name somewhere in the receiver class for that. So when they get the message in from the queue, they ask it, who are you? And the announcer is then used to announce that symbol, which causes outside the forked loop for that method to get dispatched, but just using to get dispatched and respond to a claim, a shutdown, or whatever it has to do. So lots of, trying to leverage all the little clever things we know that Smalltalk can do. And so the whole thing was basically done and delivered to him in June last year, and it's been running off and on ever since. So, it was a fun 6 months, 7 months, whatever, and got me back into doing some fun things with Smalltalk, because for the day job, I basically have to nurse a bunch of Windows machines, which doesn't make me a happy boy, but keeps me off the street. So, questions, comments, sir?
Did you look at shared memory shared memory for the different Pharo images?
No.
Into that?
No.
There was a project about 10 or more years ago where there's a squeak multi-threaded VM that could scan through it.
The guys that did that parallel computer built, there was a squeak one that was multi-threaded. Because they now have a functioning 64-bit FFI that's in reasonably good shape in version 7 of Pharo, there is some mumbling that they're going to try and actually move some of the process scheduler process parts of Smalltalk into actual outer green threads and into actual machine threads. But the debate rages about that, because then that exposes you to the vagaries of what the dispatching mechanisms of whatever both hardware and software you're on. Whereas, when you're doing it in Smalltalk, you have a known thing, right? So, no, but we did do some tests with some of his worst cases and everything to just see how much memory and how much swap and everything. We were careful to put fairly high speed SD cards in there, get the very high speed ones, so that IO is still miserable, but it's there. So if it ever swaps or whatever, that it won't be awful. There is probably a little bit of performance penalty because we occasionally do get a little swapping around the edges, but in general, the memory pressure on the actual operating system from these 4 images running has not been enough to ever crash it or anything like that, so we haven't really worried about it. Sir?
Maybe I'm missing something. This might be a dumb question, but what would have happened if instead of making 4 copies of the image, you just launched the same image file since you're not saving it?
Well, I essentially am launching 4 copies of the image file, but they're not, they're actually,
I took your diagram to mean you actually had 4 physical copies.
I do. And the reason is because they aren't actually identical. There are, when I seeded them originally, there are a couple of classes in each of them that make them unique, that stamps their ID and stuff. And I could have had like an external file that I read in on startup and, registered the class to do that and everything. I said, screw that. I'll just make 4 copies and I'll put a class in there that knows. And so as I seeded each of the ones, I went in with SSH I left it with the UI running, but nothing connect, and went in with VMC and went into each of the images and hand labeled them. You are worker 2 on Pi 3 or whatever, So that's why it was just laziness on my part. You're right. There's no reason to have done it otherwise. It was just I didn't want to write all that other code. Sir.
To solve this original interesting idea of how to take advantage of the multiple cores, have you also considered, because that was my next experiment, is to, I was running the VA Smalltalk images with Docker, and so I burned a Docker image, and then I just run it, and then in a second step I could use Docker Compose, where I could launch different numbers of containers,
Yep.
and that would also reduce the number of
It would. It would.
do you think that's a valid approach?
It is a valid approach. I was aware of Docker, and in fact, I've got a Pi at my house that is a bridge between non-Apple recognized Internet of Things like an S thermostat or whatever. It bridges them in so that the home app on your Apple stuff will recognize it. And I just got a pre-built node thing with all the stuff in there. There's a Docker image that I just literally all that has on it is Raspbian and a Docker thing. Again, old-fashioned guy and laziness. Once I had, because I was originally testing with a single Pi, in fact, the one that's on that board, and once I had that and made a clean version of it, I just sat there with my Mac and burned 7 copies of the thing, and manipulated where the files were while those SD cards were mounted on my Mac, and then stuck them in the Raspberry. So it was just, yeah, it's more manual and less glamorous than Docker, but it's also a lot less complexity. I don't have to manage the containers. I don't have to worry about it. But in terms of a way to do what I said, it would absolutely work. Yeah, and you could use this on other machine types too, right? So, for instance, now you can get fairly cheaply the new what's the name of it? AMD RIP something or other that Ryzen. Yeah, you can get fairly cheap Ryzen guys that have 48 threads in them, for $300-400 plus a motherboard or whatever. So you could build a monster on a single box, but you'd still have to do some kind of multiplexing like this until we get actually externally threaded, VMs. So.
Will anybody ever port the Pharo image to GPU, for example, NVIDIA or something, where you have lots of cores?
Not that I'm aware of. I've never heard of that project. Yeah, but you don't have the right instruction set in a GPU, right? Yeah, but again, you don't have the right instruction set for you need integers and loads and stores and stuff that it's not vector based. So that's what he was asking about earlier. In the late '80s, there was in the Bay Area startup that actually did a parallel Unix machine. I mean, the hardware of it was inherently parallelized before the days of multi-threaded CPUs and things, and they built a parallelized squeak, so they had to make things reentrant that weren't reentrant and all that sort of stuff, and they had like parallel collections and things, which to where you could dispatch a collection, it would break itself up and run on all the pieces and then collect itself back together. Think about that a bit. So yeah, it didn't go well, but it was a nice try. this was, like I said, this was the quick and dirtiest way to try to squeeze all the juice out of these things, and it worked. And again, the raspberries are another example, just like our cell phones and all that sort of stuff, where small packages, but there's really a lot of oomph, you know. And since I'm not particularly I/O constrained and not even particularly network constrained, I don't really suffer that. I'm just literally using the CPU power. So
total cost and total performance, please.
the boards, yeah, the boards, the box, not counting my time to do the construction, because that was just, I write that off on the fun side of the sheet. But the boards and all the parts to make the box and everything ran in the $300 to $350 range, okay, which is like the cost of a single motherboard, basically. And like I said, I worked on the thing between like about October and June, off and on, whether it was doing hardware or writing code or whatever. So.
And your speed improvement over the original just running on one machine, or
It's not speed, it's throughput, right? So typically at first, and I haven't asked him lately, things that would run an hour and a half on his Linux box would run in the order of magnitude of 100 to 110%. So, 3 hours instead of an hour and a half, right? Per task. But now he's got 28 tasks going on. So that at the end of a 48-hour period or 24-hour period, he's gotten a lot more done, right? Because of the cluster effect. So the cores are actually all quite a bit slower than his hub machine, but because he's got 28 of them literally running in parallel, that's where the payoff comes.
So you can split this problem up into discrete pieces that can be farmed out?
He deals with discrete numbers. It's not like an array partitioning problem. It's not that kind of thing. Each task that he distributes is a single number that he wants to do this set of operations on, okay? And one of the things I didn't tell you too is that for some of the prime number parts of this, there's a well-known C library that does a bunch of stuff, and I actually made a plugin, a Pharo plugin. So some of the things he does, and which we had already done that before we got to the cluster idea, are actually dispatched to that plugin, some of the primitive level numerical operations. It turns out that the way that integers are defined in that C library map very nicely to, there's a way to essentially do a pointer to a large integer, because they have to do the same thing, right? They've essentially done what we think of as learning as a string of digits, and they have to know how long it is and all like that. And it's very isomorphic to the way Smalltalk does it. So it was easy to hook those two things together. But that's a small piece of it. But I did actually have to build and compile that on the Pi, right? So that I had an ARM copy of it, but it worked. I mean, it's standard C. It works just fine. I'm sorry, I lost the third of your question.
I was asking if your task was to break up.
No, right. No, I'm sorry. So if you think about his task, So his task is he's got this universe of numbers that he's looking at, each one being very big, and he's got some kind of criteria that I don't understand. I don't have the math for it to figure out. He generates sets of them basically from a different process that he does, and then he sets those sets up, and the task manager in this just grabs the next one out of the pile. This is go do this one. It's 110,000 digits. I want to know if it has this, and this property. 3 hours later, he gets the answer to that. It goes in the log, and he makes the next one. When that pile starts to run low, he makes more. But each one of those, it's the same operations, but they're independent of each other. So he can hand out 4 of them, 10 of them, 1,000 of them, whatever resources he has. No. It's not like a GPU array operation where you're splitting one thing up and doing it and then putting it back together. It's not that. These are all independently, the same task being done independently on independent inputs, which is what made it easy to do, right? Is that it? All right. Thanks, guys.